I think I can maybe start presenting a little bit, although I expect everyone to know why they are there. But to recall, I mean, we're here for the senior thesis presentation of Moaaz AlQady. So this course is a capstone course in the mathematics program. It's not a required course, at least yet. It is certainly recommended for those who want to do higher studies, master or PhD in mathematics. But even for them, it's not absolutely, life or death situation. But it's certainly a good thing to try, to take this course and then, or to do this work, this thesis, as a taste of what is to come. Now I have sent the thesis itself to the written version. The presentation, the oral presentation, is assumed or supposed to be certainly less technical. It's part of the challenge, I think, to be able to convey orally to diverse audience, not completely specialized, not completely ignorant either, but not completely specialized audience in a sort of a bit more intuitive way. And it's a challenge, of course, depending on the subject. Some subjects are quite difficult to present in a more intuitive way. But somehow it gives a measure of the depth of the understanding of the speaker, in addition to maybe some talent for oral presentation or not. But so it's part of the game, of course, to the oral presentation itself. A last word, maybe. Moaaz, I think, didn't take any formal course in algebraic topology or even in topology, correct? Even not a study. And his advisor, myself, was even not that much qualified in algebraic topology. Just some basic knowledge that he had forgotten a great part of in the last years. So Moaaz had quite a steep hill to climb in order to acquire all the tools that you need to reach the special topics of these wild spaces. But anyway, you see that he has done a good job, at least in the written part. We'll see the presentation. So, okay, I leave the floor to Moaaz, who will tell us everything about the fundamental groups of wild spaces. Go ahead, Moaaz.
Thank you, Dr. Michel, for the introduction. Okay, so today we will talk about fundamental groups of wild spaces. Just a rough outline. Um, so first, I will introduce the notion of homotopy and fundamental groups, and then we will do some classical calculations of fundamental groups, mostly hand-wavingly because of the time. And then I will talk about what are inverse limits and inverse limits of groups and topological spaces. Then we will try to understand the fundamental group of the canonical example of a wild space called Hawaiian earring. And then hopefully, if time permits, I will give a quick proof sketch of one of the most important theorems on which the whole understanding of this Hawaiian earring group depends. So let's start. First, we want to, like, one of the most important goals of topology is to be able to classify spaces up to deformation. And as you can see here on the right, we want to be able to consider these two spaces somehow equivalent because they have the same basic shape. And this is a motivation for the following definition. So if we have two spaces x and y, and two functions between them, f and g, we call these two functions homotopic if there is a map from x times the unit interval to y, such that h of x and 0 is the same as the first map, and h of x and 1 is the same as the second map. So here we think of the unit interval as time from 0 seconds to 1 second, and um, so we start at f of x, and then it gets deformed continuously into g of x at time s equal 1. And here is another picture of a homotopy between two paths. So these beginning and end paths are homotopy equivalent or homotopic to each other, and the deformation is what the animation is showing. But for path and loops, we assume something extra. We assume that the endpoints are fixed throughout the homotopy, like this example, and we denote the relation between two maps being homotopic by this similar notation. And it's easy to check that this relation is an equivalence relation. So obviously a path or a loop is homotopic with itself. And if f is homotopic to g, then the other way around is also true by just thinking of the homotopy happening in the reverse time. And for transitivity also it's easy by like if we have f homotope to g and then this is homotope to h, then we can do the two homotopies one after the other twice as fast to get a homotopy from f to h. And so we can talk about equivalence classes of maps under this relation. So we say that the homotopy class of f, meaning the class of all maps that are homotopic to f. Here is another example of homotopy, but these the starting dotted path and the ending dotted path are not homotopic to each other because there is a hole between them. So we can somehow take this path to the other one without breaking it or violating continuity in one way or another. And this gives us an idea that we can study shapes of spaces by understanding uh, where do their holes occur. And, uh, and in order to measure the existence of holes, we can look at the different homotopy classes of paths. So here, for example, on the left, we have only one class, but here on the right, the above one is belongs to a different homotopy class than the below one. So notice that a loop can be represented as a function from the unit circle to our space. And we say that a loop is contractible if it can be like pulled uh, to a single point via homotopy, like this loop. Um, and so this allows us to classify spaces. So for example, on the sphere, every loop uh, can be contracted to a single point, but on the torus, this green loop and this blue loop both cannot be contracted to a single point, and this somehow is a measure of the existence of a hole inside of the torus for the green loop and like the one in the middle for the blue loop. So we define the fundamental group of X with the base point X naught to be the set of all homotopy classes of loops based at X naught. And I'm saying the fundamental group, but I'm describing a set, so we need an operation. So if we have two loops, we define their product as their concatenation. So if I have a loop like this and a loop like that, their concatenation is I go over the first loop twice as fast and then over the second loop twice as fast. And this defines uh, our operation on the loops, but we need to make it an operation on the homotopy classes. And we will do this in a minute. First, the inverse of the loop is defined to be the exact same loop, but traversed in the opposite direction. So for homotopy classes, we just if I want to multiply two homotopy classes, I pick a representative from the first and a representative from the second, and I concatenate the two and I look at the representative. So we need to check some easy stuff like that this is well defined and that it defines a group operation. But like these are easy to check. And so this gives us a mapping between topological spaces and groups. Um, so given a topological space X, we associate to it its fundamental group, which gives us information about the loops in the space, etc. And it's not just a mapping between topological spaces and groups, but it's also a mapping on the functions between them. So continuous functions between two topological spaces induce in a natural way homomorphism between the corresponding groups. And this is in the following way. So if we have a map F from X to Y, we get a group homomorphism from pi1 of X to pi1 of Y by taking so if we have a homotopy class of the loop gamma, I can compose gamma with the map F to get a loop in Y, and uh, and I take the homotopy class of that, and we can check that this uh, satisfies the homomorphism property, and also that it behaves well with composition. And by this I mean that if I have two continuous functions f and g, and if I take the induced map from their composition, it will be the same as the composition of the induced maps of the individual functions. Um, okay, so in this language, we can ask what is the fundamental group of the sphere. And this is what I was referring to earlier. I said that any loop on the sphere can be contracted to a single point, and and this means that the fundamental group has only one element or one homotopy class. So it's the trivial group. And for spaces like that, that only have contractible loops, we call them simply connected, which means that their fundamental group is trivial. So now this is a question for the audience. Probably many of you already know. Uh, what is pi1 of the circle? So for the circle, it's not like the previous spaces I discussed so far. It looks like there are some loops that cannot be contracted. So if I go around the circle, uh, there is a hole in the middle, so I can't pull this somehow. Uh, okay, I I somehow scrolled already. Okay, so the answer is it's isomorphic to the integers. Uh, and this is intuitively because I can go around the loop, the circle once or twice or three times, or I can go in the opposite direction once or twice or three times and so on. But it's more complicated than that to show it rigorously. And this is what I will try to sketch now. But for that, I need to make the following definition first. So we say that we have a map f from y to x and another map p from x tilde to x. We say that f tilde lifts f with respect to p if p of f tilde is the same as f. Um, and in diagrams, we say that this diagram commute, meaning that if I go over any path from any object in the diagram to the other, it will be the same function. Okay, so define the following map from the real numbers to the unit circle, given by the function that wraps the real line around the circle. And you can visualize it in the following picture. So imagine that the real line is wrapped like a helix above the circle, and the map P is just the projection onto the XY plane, uh, which like uh, maps to the circle sitting in the XY plane, or we think of it as sitting in the XY plane. And for each integer n, we can define a loop that traverses the circle n times. Uh, okay, and the claim is that the map that takes an integer n and associates to it the homotopy class of the loop traversing the circle n times is a group isomorphism. Uh, so first, it's easy to check that it's a homomorphism because if I go around the circle n times and then I go m times, it's the same as going around the circle n plus m times. I mean, it's not the same. Homotopy. It's homotopic to it by just like changing the speed with which I'm traversing the circles. Um, and so the proof will proceed by studying the lifts of with respect to this map P of these loops Fn. So this map F tilde sub n defined by nx gives us a lift of the map n. So visually, if visually if I'm starting all my loops at this point, and the loop traverses this circle say once, then the lifted map starts at this point and uh, goes like this until 1. So this is 0, this is 1, this is 2, and so on. And it is a lift because if I project, I get the loop, or also you can do it algebraically. Um, so now suppose that I have proved this fact that I will not prove, but like I will give an intuitive sense of why it should be true. So this property says that any loop or a path in the circle below lifts to a unique path uh, that starts from a given point, say 0 in this case. And and the reason for this is because if say I'm here and I want to lift this loop, I will go a little bit like this, and then at each small neighborhood, I don't have a choice of where to go. I have to go like to the next little bit, so on, and so I will end up traversing the exact same loop. Uh, and the other property is that if I have two loops that are homotopic in the circle, and I left them to the two paths, uh, then these two paths will be homotopic, and the homotopy in the real line will be a lifting of the homotopy below, and in particular, the endpoints of the lifted maps will be the same. Uh, so I will skip the proof of these facts, but these are like the core properties that we will care about for this proof to work. And so now I can define a map from the fundamental rule of the circle to the integers by taking any loop f and taking any homotopy class and pick a representative, lift it to a path, and choose its endpoint to be the image of this homotopy class. So for example, here this loop that winds around the circle once, its image would be the number 1. If it winds around the circle twice, it would be 2, and so on. So psi will be well defined on loops because on homotopy classes because we said that first this f tilde of 1 is well defined because we said that paths are lifted to uniquely to a single path, and it's defined on homotopy classes as well because we said that homotopic loops left to homotopic paths. So in particular, they have the same endpoints. And notice that we have psi of f of n is the same as f tilde sub n of 1, which is n. So psi of phi is the identity on the integers. And so we only need to show that psi is injective. Um, so this is because uh, if I have psi of f the same as psi of g, then f tilde of 1 is the same as g tilde of 1. And so they end at the same point. So if this is f, for example, and then g also ends at the same point, if I do f and then do g in the other direction, or like the inverse of g, it will give me a loop in R. And the following homotopy can deform any loop in R into the trivial loop. Uh, in other words, R is simply connected. And this means that uh, G tilde inverse after F is connected. And so applying the fundamental group to the whole map uh, tells us that the homotopy class of G inverse is times the homotopy class of F is the trivial homotopy class. And this means that F and G are homotopy to each other. So this completes the proof. And notice that the main things that we needed for this to work is the path and homotopies are lifted to unique path and homotopies, and that the real line was uh, simply connected. And so we want to generalize this strategy for other things as well. So consider the following definition. We say that a covering space is a map satisfying the following. So for every point x, there is some neighborhood u such that the pre-image of this u is a disjoint union of neighborhoods in x tilde. And each of these open neighborhoods is homeomorphic to the, the neighborhood we started with. So notice that this is the same situation as the map P we had before. So we are trying to generalize the same thing. And it turns out that the path lifting and the homotopy lifting properties also work for any covering space. Uh, and we make also the following definition. So we say that a universal covering is a covering space that is simply connected, or rather, the map x tilde is the space x tilde is simply connected. So if we have these two parts, then we can make sure that the same strategy we used for S1 works for other spaces as well. And so the question now is, what are the, the spaces that have universal coverings? And these spaces are characterized by the following two properties. First, they are path connected and locally path connected, which means that if for every open set U of X, there is a path connected open set V containing X, V being subset of U, such that the smaller set is path connected, and the space is locally path connected if it's locally path connected at each point X like this. We will not care very much about this property because all the spaces we will consider are locally path connected and path connected. But this is the defining property for wild spaces here. So we say a space is semi-locally simply connected if uh, every point uh, every point in the space there exists a neighborhood small enough so that any loop in this neighborhood can be contracted to the single point x. And and uh, and the theorem says that if our space is path connected, locally path connected, and semi-locally simply connected, then we have a universal covering, and the we can calculate fundamental groups in the essentially the same way we described. Now, what are the spaces that are not semi-locally simply connected? So this is the canonical example of such space. Notice that at this point here, no matter how small the neighborhood I take is, I will always find loops that cannot be contracted to a single point, and and uh, and these are some other wild spaces. Uh, by wild, I mean not semi-locally simply connected. And notice how they are like always have something to do with the earring, and this can be also made rigorous. So the earring is somehow a test space for the failure of other spaces to be semi-locally simply connected, and this is why we will focus on it for this talk. So what we want is to be able to calculate fundamental groups of these weird-looking spaces. So first, I will also mention fundamental group of these spaces called wedges of circles. So a wedge is the union of two spaces being identified at a single point. So here we have two circles, A and B, and they are identified at their base point here. And this graph here, which may be familiar to you, being the Cayley graph of a free group, uh, is actually a universal covering of this space. And the universal map, what it does is it sends every vertex to the base point, and then after the two vertices get identified, the edge between them becomes a loop. So if the edge was horizontal, we map it to the loop A, and if it was vertical, we map it to the loop B. And you can check that this is a universal covering and do a similar calculation to the earlier one to show that the fundamental group of the wedge is uh, is the free product, the free group on two generators. Uh, and as a recap, if you don't recall or don't know what the free group is, it's basically the set of words in in two letters. So, for example, x, y squared, x squared, y inverse is a word in this group. Um, it can be something like x like this, but we can always combine them to be of this form of an alternating product. Okay, and similarly, the fundamental group of the wedge of n circles is the free group on n generators with like exactly the same idea, but like the the fundamental like the universal covering, for example, for the wedge of three circles would look something more like this, so on, and for each other like it, they all look pretty much like the same idea as this. Um, so at first glance, one might think that the Hawaiian earring is the same as the wedge of countably many circles or countably infinite many circles, but this is actually not true because uh, the Hawaiian earring is a closed subset of the plane, and it is also bounded. So by Heine-Borel theorem, it is compact. Um, Whereas the countable wedge of circles is not compact because uh, if I have like wedge of some circles like that, I can take uh, an open cover of the wedge, which in which every open set covers exactly one of the circles, and then or exactly one full circle and little parts of the other circles. So this cover obviously doesn't have a finite subcover, uh, which is exactly what it means to be not compact. But still, the wedge of circles will help us understand the groove area. And to do this, we need to introduce the notion of an inverse limit. So we will come to think of the Hawaiian earring as a limit of these wedges of circles. Uh, so we will make the following definition. Uh, let's look at this diagram instead of the other one. Think of these x1, x2, xn, so on, for now as being sets, and we have functions between them, f1, f2, and so on. We say that a space or a set X is their inverse limit if there are functions g1 from x to x1, g2 from x to x2, and so on. So that if you give me any other set x prime with similar functions, uh, g1 prime from x prime to x1, g2 prime from x2 to x prime to x2, and so on. And yeah, and there's also one condition I forgot to mention that uh, these maps should be compatible with the functions in the line below. So by this I mean that if I do f1 after g2, it should be the same as g1. If I do f2 after g3, it should be the same as g2, and so on. So if I have a set like this, if I have another set x prime like this, I should have a unique function from x prime to x. So this is what's called a universal property for the inverse limit. So in some sense, x is a universal object among uh, all other uh, all other such sets with such compatible maps. Um, okay, but we can also characterize it in a more like explicit way as a set by thinking of it as a subset of the Cartesian product of all these sets x1, x2, and so on. So it is the set of sequences x1, x2, etc., with x1 being in capital X1, x2 being in capital X2, and so on, so that it satisfies that if I have, say, here little x2 and here little x1, then this function f1 should map x2 to x1, and similarly x3 is mapped by f2 to x2, and so on. I think this should be a plus, not a minus. Okay, and what are the maps g1, g2 in this case? They are the natural projections which pick the first coordinate for g1, pick the second coordinate for g2, and so on. And we can check that this set here satisfies the universal property we talked about. So this construction doesn't only work for sets, it can also work for groups and topological spaces. Uh, and by work for groups, I mean that if we think of the axes here as groups and the maps between them as group homomorphisms, then the same universal property would apply to this set, where this set inherits the group structure from the product. In other words, the operation being component-wise multiplication. Um, So as an example, consider the three groups we talked about earlier. So this is the group containing words in one letter. This is the group containing words in two letters. This is the group containing words in three letters, and so on. And their inverse limit is um, a subgroup of the product of all of these, which consists of sequences of words that satisfy the that is satisfies the condition we talked about, which in this case translates to if I delete the letter A2 from my word everywhere, uh, I will end up with the previous word. And if I delete A3 here, I will end up with the previous word again, and so on. So this is the inverse limit of three groups. And for topological spaces, there are also inverse limits, and again, the same construction works as subspace of the product of all of the spaces. So as an example, take x1 to be the wedge of one circle, x2 to be wedge of two circles, x3 wedge of three circles, and so on. And then their inverse limit is some space, okay? But then notice that the Hawaiian earring has natural maps into each one of these, uh, which is compatible with the maps here. I forgot to say that the maps here are, so this map here collapses the second circle into the base point. So this circle gets mapped to the base point, and the outer circle is mapped homeomorphically to the circle we have. And similarly here, the third circle is collapsed to the base point, and the other two circles uh, mapped onto the other two circles, and so on. So the Hawaiian earring also has maps into each of these, and it is compatible with the maps of the inverse system below. So the F1, what it does is that it collapses all of the circles of the earring except for the first one. F2 collapses all of the circles of the earring except for the first two circles, and so on. And so by the universal property of the inverse limit, we have a map from the Hawaiian earring to the inverse limit of these spaces. And it turns out that this map is actually a homeomorphism. Uh, I mean, it's injective and surjective. It's not hard to see why, because um, well, elements in here are, so this map F maps an element, maps a point on the earring to, so if this point lies on the nth circle, point X lies on the nth circle, it's mapped to the base point for all the first circles, and then to itself in the starting from the nth position. So if two points are mapped to the same sequence, they must lie on the same circle and they must be exactly the same point. So it's injective, and it's surjective because, well, any sequence like this has a point corresponding to it in the earring. And it's also a continuous function from a compact space to a Hausdorff space. Um, and so it's a homeomorphism. Okay, so now we talked about the inverse limit of these spaces, and it turned out to be the earring, and we also talked about the fundamental group of each one of them. We know that the fundamental group of this is F1, the fundamental group of this is F2, and also that these maps, binding maps between them, are the same as the maps we talked about for the for the free groups. So removing the second circle, for example, is the same as, or like collapsing the second circle is the same as uh, deleting all instances of the second generator of the free group, and so on. So so there's now a natural question of whether the inverse limit, whether the fundamental group of the inverse limit, which is fundamental group of the E-ring, is it the same as the inverse limit of the fundamental groups? And the answer is no. Uh, Life is harder than that. But still, these uh, like thinking this way can lead to fruitful direction. Um, so if we apply pi one to all of the diagram we had before, we get pi one of x1 is f1, pi one of x2 is f2, and so on. And we also get from the maps between the E-ring and x1, we get induced maps from pi one of the E-ring to pi one of x1, pi one of x2, and so on. And so by the universal property of the inverse limit of free groups, we have a canonical map psi from pi one of the E-ring to the inverse limit of free groups. And we can ask ourselves, okay, this map may not be an isomorphism, but is it surjective? Is it injective? And so on. So first,
Sorry,
let's
what was F1?
F1 is the free group on one generator, which is basically the integers.
No, I mean small f1, the map from the fundamental group of H.
Okay, so F1 without F1 itself was a map from the E-ring to X1, which what it did is collapsed all the circles in the E-ring except for the first circle. So F1 hash is the induced map, uh, which we okay. So what it does is um, so if we have a loop in the Hawaiian E-ring, which like traverses some of the circles of the E-ring, we only look at how many times it spans the first circle, and uh, and this tells us whether it's a squared, a cubed, and so on. And like similarly for F2, we only look at like we consider the loop to be constant on all of the like if the loop, for example, traverses the first circle, the second circle, the third circle, and then fourth circle, and then again back to the first circle, we consider it to be constant in any loop except for the first circle.
Yeah, I see.
Okay. Um. Okay. So let's take a closer look at the
Could
loops.
be, maybe it would have been, I don't know, it depends if Dawood or other asked the question as a, what exactly is this function, but the point is that the pi one is a functor. So necessarily if there exists a f1, then there will be a f1 dash, which will be just pi one of f1, you know, it will just be the image by the functor. So we know there exists something there.
Yeah, I was trying to imagine its description. Like it takes loops in the earring, in the Hawaiian earring, and send it to maybe, as Mara said, just neglecting loops not in the first loop.
Correct.
Yeah, exactly. So yeah, so what we care about most is that there is something so that we get the induced map. Um, okay, so what do loops in the Hawaiian group look like? So the problem is that they can look pretty nasty. They can traverse infinitely many circles. So for example, we can have a loop that traverses the 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 first circle in the first half of the interval, and then the second circle in the like, next quarter or something, and then the third circle, and then the fourth circle. So it can traverse all of them and still be continuous. So with such while loops in the Hawaiian group, we have a pretty big fundamental group. It's in fact uncountable, but I will skip the proof because I'm running out of time here. Uh, okay, so psi is not surjective actually, and here is why. Uh, so suppose that it were surjective, then the inverse limit of the free groups contains the following words: uh, G1, G2, G1 inverse, G2 inverse, G1, G3, G1 inverse, G3 inverse, and so on. Uh, I mean, this is Wn if we take the sequence in the inverse limit that corresponds to the limit of these words, it will be like a transfinite word uh, which contains the generator G1 infinitely many times. And and so if we look at the so if we have this loop and call it gamma, and we compose it with a map that only picks the first circle, we will have a loop in S1 or in X1, which traverses the circle infinitely many times. But this cannot happen. It violates continuity because if we take this loop and so we have a loop in S1 gamma, we can lift it with respect to the universal covering we had before, and this will give us a map, a surjection from 0, 1 onto the infinite the non-compact interval from 0 to infinity, which is impossible, of course, because this is compact. So this element cannot be in the or like the loop corresponding to this transfinite word cannot be uh, in the image of psi. Um, okay, so this gives us an idea of what kind of loops we have to exclude. So we have to exclude uh, the words in which there is some letter that appears infinitely many times, or rather the sequences of words such that there is some letter that appears more and more the more we go into the sequence. So we call a sequence locally eventually constant if uh, for any letter, for the kth letter, its number of occurrences in the words W1, W2, and so on becomes constant after a while, so it doesn't grow and grow to infinity. And a set of locally eventually constant sequences form a subgroup of the inverse limit. It's called the sigma free product of the integers. And uh, and it turns out that this is exactly the image of psi. So phi 1 of h is uh, maps onto this subgroup, and it will turn out also to be that this mapping is injective, uh, but this is like the big theorem of the whole topic. So I'll keep this for now. So first, let's look at why it's surjective. First, uh, if we have some word that is not locally eventually constant, we will run into exactly the same problem we had before. We will have a loop that traverses some circle infinitely many times, and so um, it will violate continuity. Conversely, if we have a word that is locally eventually constant, then we can always find a loop that corresponds to it, and this is done in the following sneaky way. So consider the contour set, and let's look at its complement in the unit interval. So I'll work on this third iteration. That's enough for illustration. So we have a couple of open sets like this, and in the limit we will have countably many open sets, and they are dense in the sense that between any two open sets I can find another open set, and between any two open sets I can find another open set, and so on. So no matter how convolutedly nested the transfinite world I'm trying to map to is, the intuition is that I can always go into higher and higher iterations of the contour set to find open sets and squeeze in the loops I want to make in whatever order I want them. And this can be made like more rigorously in the language of order theory. So it's basically because these intervals have the order type of a dense order, and so any other order type that is countable injects into it. Um, okay, so now we now calculated the fundamental group of the E-ring as this subgroup of the inverse limit, pending the proof that the map psi is injective. And as I said, this is a highly non-trivial theorem. I'll try to give a super quick overview of why it is, of how the proof goes. Uh, and like for anyone who's interested, you can like look at the paper closely. So the idea is that we have this approximating sequence of the Hawaiian earring, um, and each of these spaces has a universal covering. So we said that the circle has a universal covering, the R thing we showed before, and this is the wedge of two circles has a universal covering, the free product we showed, and so on. And each of these universal coverings is a tree. So the idea is that we want to take the inverse limit of these universal coverings and get something which is not a universal covering. It's not even a covering, but it will have some nice lifting properties still that will help us prove that psi is injective. So first we will have to use the following theorem. So there is a theorem that says if I have a map, in this case P2 followed by R1, and it induces a map on the fundamental groups, which is inside of the image of another map of the induced map of another map on fundamental groups also. Then we have a lifting. Okay, this doesn't make much sense. If I have a map like this between two spaces, and I look at the induced map on fundamental groups, if it if the image of this group lies inside the image of the map induced by the universal covering, then we have a lifting to the universal covering. So this is what we have here. This is simply connected. So this followed by this is mapped to the trivial element, and so it's in the image of P1 hash, and so we get an induced map like this. Similarly here and here, so we get an inverse system on the universal coverings. We take the inverse limit of the system, but the inverse limit has projection maps like this, which after composing with the maps P gives us a map to the inverse limit of the axis um, by the universal property. And now this inverse limit, we can prove the inverse limit of trees contains no simple closed loop. But it might not be connected or fast connected, but we can take like a path component of it that contains our base point and okay, and restricting this map gives something which is not a universal covering, but it's nice enough that we can make uh, uh, we can have like lifting properties that we need. And finally, if we want to show that the psi is injective, we want to show that its kernel is trivial. So if we have a loop in H with its projections being trivial, we want to show that this loop gamma is itself trivial. So the idea is that we left all these loops and we get an induced loop in this space H tilde. And finally, the proof uses another also non-trivial theorem that says that the image of the interval in a space that contains no simple closed loops is contractible, which means that this loop is contractible, which means that gamma, which is P of this loop, is also contractible. And this finishes the proof. And that's it. I know this last part was super quick. Sorry about that.
Thank you, Moaz. Is there any question of any order?
I have a simple question about. So you showed that the Hawaiian earring is homeomorphic to the inverse limit of the x1's xi's, right? So
Yeah.
I just missed how you defined the Hawaiian earring in the first place, like H.
Sorry. It's defined as a subspace of R2. So it's I take so this is the origin 0 0, and I take a circle of radius 1 centered at half the circle of radius uh, half a circle of radius third and so on, and they're all touching at the origin.
And then you take the union and the
And
subspace.
then yeah, exactly, I take the union.
And then okay, and then the other question, can you just restate the inverse limit universal property just to, so you say
Okay, so
like, how you start with the system below, right, with the x1.
yeah, exactly. So I start with a system of objects, which can be sets, groups, or topological spaces, or anything. So I have objects like these and functions or maps between them, and the inverse limit is another object which uh, which comes with maps into each of them. So
Okay, so yeah, so
maps
the
like
inverse
this.
limit comes with maps. Yeah.
Exactly, yeah.
Yeah.
And and these maps are compatible with the inverse system in the sense that if I do this, then that, it's the same as doing the first one, and so on. And finally, it has a universal property, which is that if I have another object x prime with similar maps also,
Which come
then I have a unique map from x prime to x, making everything commute,
nice.
which is like summarized in this diagram.
Yes, yes.
Now we sometimes abuse the language by saying, thinking of a limit or a colimit as being an object, but in fact, it's a diagram,
I see.
Yeah.
It is terminal or initial in the family of all diagrams of the same sort. Blah, blah, blah. Maybe when you're asking for the description of H, the Hawaiian ring, it's interesting maybe to compare it more with the wedge. You think of any the numerable number of circles in the plane, and even touching only one point, one common point, tangents or some, or, well, I won't say tangent now, but yeah, a tangent between each other and at one point, one single point. Then you think of the wedge also, and then what is really different from them is that, in fact, the wedge cannot be even seen as a subset, as a subspace of R2, correct? When it's infinite, I mean. You had the example of two, wedge with S1, wedge S1. But take an infinite number of them, then you're running into trouble. Or, somehow you cannot see anymore it as a subspace of a R2, correct?
I mean, definitely not as a bounded subspace of R2, but not as a subspace of R2 at all. Not sure.
Well, it's even a subset of R2 is sort of problematic the way you you can describe it. But otherwise, you think, yeah.
Aren't they a countable collection of wedges? So I guess you can put a circle inside a smaller and inside it a smaller circle. Keep going like this. So maybe
But it will have a different topology if you make the circles shrinking. The topology will be different from
Really?
from the topology that comes with the wedge.
I want them to intersect at more than one point. It gives sort of problematic deformation, which would become weird somehow. And definitely they are different because, one is not compact and the other is, so.
Yeah.
But I think the only way to define the wedge is, by sort of universal property, or as it's the copra,
Yeah, exactly. Yeah.
all the injections continuous, and then you see that there is a problem of
Yeah, or as the quotient of the disjoint union of
yes, yeah. Depends of how much you feel more
on your taste.
yeah, or comfortable with, the description.
Yeah.
But yeah, they are different. Yeah, Hussein, when you said one inside each other, what do you mean? They will, of course, if they touch if they are.
Yeah, they touch it.
Yes, but they are of different size or the same size, or
different sizes. Yeah.
Okay, but that's H. That's the Hawaiian ring. That's what you mean?
Yeah.
Yeah, of course. But the other is more problematic to represent, somehow. I have a geographical question. Is there any Hawaiian ring in Hawaii?
I saw pictures of Hawaiian earrings on Google, which looked like the Hawaiian earring, only not countably infinite.
Yeah, trust me, yeah.
I'm not sure if they are in Hawaii or not.
Good. Okay, then. Too bad that we didn't have time to look at these archipelago or the other example of wild spaces, and to give
Yeah.
the idea. But yeah, it is a bit difficult to go through all that without.
Yeah. I especially wanted to say some things about the archipelago, but wouldn't have been possible.
That's a problem.
It's even weirder than the earring.
Yeah. At the same time, if you're too fluffy, then it becomes not very serious, and it's not really giving an idea of how it really works. you had become too much and then it's not just maybe more fun, but not very very mathematical at the end. Good. Thank you, Mark.
I just have one comment.
So
First, Moaaz, thank you for this work and this thesis. So I think this is a very advanced of an undergraduate level. So thanks a lot for this hard work.
Thank you. Thank you all for coming.
And I think some students here are still younger students. So would you, in 1 minute, say, so most of the objects in Moaaz's presentations, like capital X and capital Y, these were topological spaces. So would you informally say what is a topological space, like just very informally, and just give any famous example, like the real line of, or any topological space, just to give the younger students some tangible sensation of a topological space. So just in 1 or 2 minutes, like what is a topological space?
Okay, so basically, okay, so a topological space is somehow generalization of geometric space. So geometry is more strict than topology in a sense. So if we have like a metric space or something which has like notion of distance and angles and so on, that's somehow more strict than topology. Topology is just about having a set of points and forcing some points to say that these points are near each other. So we think of having some set of neighborhoods, saying which points are near which points. But we don't have like a rigid measure of distance. So, so the spaces I was dealing with today are like some of the nicest topological spaces. And like topology is known for you can have like very counterintuitive spaces or like things that we wouldn't necessarily think of them as geometric. Yeah, so the idea is that we want to be able to study things like continuity in its with the absolute bare minimum of definitions on our space. So like we can define continuity easily with having a notion of distance, but somehow mathematicians wanted to think of like the least possible structure we can have to in order to to be able to define topology and like try to push the limits of what we can do with like the minimum possible thing, or at least this is how I think about it. I don't know if this makes much sense.
Yeah, it's a bit difficult. It was maybe a difficult question. There are many ways to answer that, I suppose. You think of in mathematics, we often start with very concrete examples, R2, R3, etc.
Yeah, this is what I just wanted to say to other students that the real number line, the real plane, or the
Sorry, I understood
these are topological spaces that you are familiar with.
Yeah,
And
exactly. So anything with a notion of distance is automatically a topological space.
Yeah. And as Maya said, like the idea of a topology is to say which points are close to each other, and without so by giving without using a distance. So you just claim which subsets of your set are close to each other. Yeah, Michel, sorry, what are your
No,
other?
I mean, it's you're right. I mean, we would have also start with the very concrete or habitual or usual spaces like R, R2, R3, and the idea of continuity and the feeling you had of continuous movement, etc. And then you, as Moaz said, you sort of stretch this idea to the extreme, but also somehow in order to have the wonderful theorems that you had in this concrete context, to extend it, to the extreme limits, and then what do you need exactly? What sort of tools or definition do you need to have the theorem as stated to be right, still right, and then you can, of course, that's where abstraction comes from. Of course, in practice, it comes from also some use, sometimes you need spaces which are more general than points in R2 and R3. You may need functions themselves as being points of a new space, and then the theorems on continuity, you want to mix them there so that big theorems would work, and you can extract properties of a more general framework. And then if you have people crazy enough to push it to the extreme, then it becomes something totally impossible to represent, in a picture, but sort of algebraically, it still works. And then it can be useful in sometimes unexpected areas. And I know Hussein may have another vision of all that, another way to start, and anyone would have experience in a bit in using topology or topological thing, you would have a different vision of that. But if you think of ring theory, for example, or groups, or rings starting with Z, integers, then you try to extract from it, completely abstracting not all, but much of what is true there to the extreme, then you get with algebraic structure, which have very little to do with Z at the end, but then for which some theorems are still true, and you exploit this line somehow. Sometimes motivated by concrete examples, but have very little to do with the original.
And also, like the prize we get from this high level of abstraction is that, like, if we have something that is very general, like a topology is, like we find it popping up in all sorts of places. Like, rather than looking for a geometric space somewhere, it's easier to find topology lying around. Like, for example, those who took algebra, for example, the ideals of a ring have some topology on them, which Hussein can tell you all about.
And then logic, like Dawood would know, that some sets of formulas or structure may have, the topology that comes sort of naturally in them. If you define topology in general enough,
The topos.
Yeah, the topos also, but even more, a simpler examples would be just a set of all sentences, which etc., with some equivalence class, and then you get, there's a famous compactness theorem in model theory, which speaks about the compactness of a certain space of sentences, etc., or class of spaces. So you define the thing as like some crazy idea, and then suddenly you find it can be used at bizarre place that have nothing to do. And then it is fruitful sometimes not.
Dr. Michel, can I say one thing about Moaz's talk? So I liked it a lot because he told me that and in his written part, he showed actually that the fundamental group behaves very nicely under co-limits. But this is the counterexample to behaving nicely under limits. So that was really nice to see as a concrete example of that. Unfortunately,
Yes.
the time I think was too short to talk about co-limits and all this stuff. But that was a very important example, I think.
It's an interesting remark because although unfortunately the fundamental group functor does not preserve co-limits as such, but it preserves some and it behaves better. Like algebra is what behaves very well with limits, products and, of course, pullbacks and these things. I mean, for algebraic structure, they behave, sort of trivially, very easily, or they behave well, let's say. But co-limits are, you know, the co-limits of groups is not as trivial, you know, push-outs are amalgamation, is a bit complicated thing. But limits are, but for topology, it's sort of the opposite, not exactly the opposite, but you're right. I mean, it's sort of, yeah, the well behavior is the other, or the interest is on co-limit sometimes. But that's the Van Kampen theorem somehow that Moaaz didn't have time to expose, but which is you had to study and to struggle with at some point. Yeah. It's about push outs and co-limits. Yeah. Yes, good. Are you doing a lot of category theory, Hussein?